continuing the dot product, this is the alternate form of the theorem up here, which helps you find the angle between two vectors. I just wanted you to see an example of using that alternate form of the theorem, and you typically use it when they're asking for a dot product, but they're not giving you the component forms of the vectors. And, you know, like, well, how do you get the dot product if they don't give you that? Because, you know, it doesn't look like you can do it. Turns out you can use this if they give you magnitudes and the angle. So here's an example. Let's say, this is the question, not in your course reader. Let's say somebody told you a vector u had a magnitude of 2. And let's say also some other vector, we'll call it v, had a magnitude of 3. And the angle between the vectors was pi/4 radians. What is the dot product? U dot v equal to? Oh boy. Well, unlike the other examples we did from last time, you can't use the definition of dot product where you take the sum of the products of the components, because they didn't even give you component form. And you can't get component form because, you know, I know some of you said, well, you told us that we have an angle and we have magnitudes, we can resolve it. Yeah, but this is in 3D, and that resolution of a vector into its components was only valid for 2D, not for 3D. I better not catch you trying to do it for 3D. Oops. You know, so if I were to draw a picture of this, and I'm just going to draw some cheesy picture, you know, you'd have you know, pointing off in some weird direction, let's just say there, and it's got a magnitude of 2. And then V is pointing off and making an angle of 45 degrees. So V would be like, you know, this angle here is 45 degrees. V is a little bit bigger than you because its magnitude is 3, and they want you to find the dot product. So you're just going to use this alternate form of the theorem. You're going to go, oh, well, the dot product is cosine of the angle between them multiplied by the product of the magnitudes. Oh, easy peasy, you know. And I think cosine of pi/4 isn't that hard, square root of 2 over 2. And then you can reduce this to lowest term. And final answer, it looks like the dot product is this irrational number, 3 square root of 2. That's totally legit. And so we're done. And that's dot product in an alternate form. Okay, so you got to see that. Now let's talk about another application of the dot product, specifically projections. So how do you do a projection and what does it look like? I'm going to draw you pictures of projections first so you get an idea of what a projection is. It's really important for you to get projections. I will be asking you to sketch diagrams on future quizzes and exams when it comes to projections. So I don't ask a lot of sketchings in this class, but there are some that I will be wanting you to do, okay? So let's start. Projections and vector components. So let's have a couple of vectors that are non-zero. So, you know, they're somewhat interesting. And moreover, U is going to be the sum of these two other vectors, W1 and W2, where W1 is parallel to V, which means it makes either an angle of 0 or 180 degrees with V. And W2 is orthogonal to V. What does it mean to be orthogonal again? It would make an angle of what?
Perpendicular?
Yeah, perpendicular. So what's the
90 degrees.
Yeah, 90 degrees. Okay. So it also means that the dot product would be 0. Orthogonal. If two vectors are orthogonal, you're guaranteed that the two vectors make a dot product of 0. And that's the official definition of orthogonal, not perpendicular. Okay, so let's do a picture. Say that let's say I'm going to do 2 diagrams. Let's say V is there, and let's say U is right here. Fine. Now, these can be vectors in any dimension, okay? Now, the projection of U onto V is going to be a vector that's parallel to V. So this is how I like to think of it, because, and I'm not trying to be ridiculous here, but it helps me think of it this way too. I pretend that V is on the ground, whether it is or isn't, but I just kind of think, oh, there's a ground. And I pretend there's a really bright sun shining up here. If you can imagine the bright sun. And the shadow that U makes on the ground is the projection of U onto V. So if you can imagine that the shadow that U makes on the ground, which would be this vector here in pink, that's W1. And that is the projection of U onto V. So fill in this blank in your course reader here. W1 is called the projection of U onto V. It's also known as something else in other textbooks, and you want to be clear if you're reading some directions. It's known as the vector component of U along V. Sometimes they call it that, but it's a projection. Now, the notation is a little bit odd. You're going to use the letters PROJ, short for projection, proj. And then when you project U onto V, U is on the same line as the projection part. And V is this teeny tiny subscript that's a little bit lower. Okay, it's a subscript. So that's the notation, projection of U onto V. Be careful, because the projection of U onto V is not the same as the projection of V onto U. So if you get confused, that's where I don't give you partial credit. You do it backwards. Yeah, sorry.
Wait, so, is that a W for the projection?
W? This is the projection of U onto V. And okay, we're naming it W1 just to give it an easier name, but it's the same. So W1 is in fact the projection of U onto V right here. Does that help?
Yeah.
Now, what about this other vector they want? Something called W2. What's him? Well, he's not a projection. He's another vector. He's the vector that's orthogonal, so it makes a 90-degree angle with the V vector. And it's such a way that W1 and W2 have to add up to W1. So remember the parallelogram law. If you think of W1 and W2 as adjacent side lengths of a parallelogram, and then the dotted lines here are the other sides of it. Well, that's a rectangle. Well, a rectangle is a parallelogram. And then the sum will be the diagonal of that parallelogram. So you want U to be a sum of the W1 and W2. Now, our physics brethren do this all the time. Our physics brethren are very interested in resolving a vector, in this case U, into a sum of two other vectors, where those two other vectors are orthogonal with each other. Okay, this is very common in physics. They do it a lot. Why? We're going to do an application today, don't worry. So this W2 is really easy to get once you've gotten a W1. I haven't given you the formula for W1 yet. I'm just drawing pictures. But if you were able to get the W1, W2 is super easy to get, because you just take the vector U and you subtract your W1. And this is called the vector component of U orthogonal to V. The W2 is known as the vector component of U orthogonal to V. I'm going to draw you another picture just because you should know another picture. So what if V is still on the ground? Here's V, you know, he's lying flat on the ground. But what if you were making an angle that's obtuse? So it's larger than 90 degrees. So this angle here is no longer acute. You got this long, you know, over 90-degree angle. What would the projection of U onto V look like now if this were the case? Well, Again, I like to imagine a really bright sun shining up here. And what would the shadow of you look like on the ground? So now the shadow of you will look like this. Well, it's pointing the opposite direction of V. This is our W1. I know, but it's still parallel to V, and that's all you care about. You want it parallel to the ground, so you're good. And then W2 will be the orthogonal component here. And you want the W1 and W2 to be orthogonal with each other. And so that's the picture of projecting when you're projecting a vector onto another vector, but the angle between them is obtuse. I just want you to see all the possibilities. Okay, so now let's get to the big formula. Okay, so W2 is easy to get if you have W1, but W1 is the hard one. So how do you get W1? You're going to use one of two handy formulas, and I don't care which one, but you're going to go proj of U onto V is going to equal a scalar, which is in parentheses here, the scalar, multiplied by a vector. So the end result is a vector. And the vector that you're going to multiply the scalar with is V. It's the vector that you're projecting onto. So don't get this backwards. So this scalar is going to be a fraction. The numerator will be the dot product of U and V. Aha, there's another application of dot product. And the denominator will be one of two things. It's your choice, okay? I'm old school, so I tend to use the magnitude of the V squared. If you prefer, you can use this formula. You'll still have U dot V in the numerator. And the denominator will be the dot product of V with itself. Does anybody remember that last time we did a theorem where, and I even proved it, where I showed you that the magnitude of a vector squared is equivalent to the dot product of that vector with itself? So it's your choice. I'm going to give you a third way to find the projection. Not my favorite, although Briggs uses it on occasion in some of the view an example button things. If I catch you using it when you don't need to use it and you're wasting valuable time, I won't give you credit. So only use this if this is the last stop on the block, which is like pretty much never. Okay? But I just want to show you why it works. Okay, so this Briggs way here, you're still going to have a scalar times a vector. Okay, so I'm gonna derive it. I won't give you the full final version yet. Let's say you start with mine, which has the denominator is the magnitude of the V vector squared, and then let's use the formula for dot product in that theorem that we covered last time. The dot product of a vector U and V is equivalent to the cosine of the angle between the vectors multiplied by the product of their magnitudes. Okay, cool beans. And then reduce this to lowest terms. Really? Does anything cancel? Do you see anything that might cancel?
No.
You can factor out one of the magnitude of V's and then reduce this to lowest terms. And so the scalar that you get looks like this times your vector V, okay? So I want you to see that another idea of this, and I'm not doing anything different here, so don't get too alarmed. I'm going to move this denominator underneath the V, and I want you to notice that this is the unit vector pointing in the same direction as V, and it's being multiplied by this scalar. Interesting. Now, I rarely use this version for projections, okay? I want you on quizzes and exams to use one of these two first ones that I have there, please, if you want maximum points. Now, what about the scalar component of U in the direction of V? Well, if I take my version and rewrite it, where I slide one of those magnitudes, I have two magnitude factors down below, magnitude of v squared. But what if I put one of them underneath the vector v? So it looks like this. This is again the unit vector pointing in the same direction as v. So the scalar component, which a lot of times they'll go SCAL UV, they may use that notation. It's the scalar that you can cherry pick off. So there's two versions of it. That version, which should be equivalent to this scalar multiplied with the unit vector for v. So either one of those formulas is going to give you the scalar component of u in the direction of v. So we're going to do some examples here, so don't worry. So in this next example, example 3, you have two vectors, u and v, and they want you to do some stuff here. Okay. So find the projected vector of u onto v. So to be in alignment with my diagram on the previous page, this is not really Briggs notation, but I like to call it W1, but it is projection of u onto v. And using the formula is you got a scalar times a vector for an ultimate result as a vector. So I'm going to take the product of the x components, 3 times 7, plus the product of the y's, -5 times 1, plus the product of the z components, 2 times -2, all over the square root squared. And then this is multiplied by v. I'll just leave it as v for now, and then I'll bring them in later. So v's magnitude is the square root of 7 squared plus, 1 squared plus 2 squared. 49 plus 1 plus 4. So what's that? 54, huh? And then when you square root something squared, you just get the thing. So what do we have here? We have 21 minus 5 minus 4. So it looks like the dot product is 12 all over 54 times the vector v. Try and reduce your fractions as much as you can. So when you reduce 12 54ths, I think both of those are divisible by 6. Yeah, you get 2/9. So 2/9 v. And that will be 2/9 times the vector with components 7, 1, -2. And then please distribute your scalar to finish it up. So I get 14/9, 2/9, -4/9. That is the projection of the vector u onto the vector v. Okay, and we're done with letter A. That's the answer to letter A. That's the projection. It's a vector. Now, in letter B, they say find the vector component of u that is orthogonal to v. What are they asking for there? Well, if you look back at my diagram, they're asking you for W2, that vector component that's orthogonal to v. So it's this orthogonal component, the other guy. And it's really easy to find W2. You use this handy formula. W2 is your original vector that you're trying to project somewhere, minus W1, where W1 is the projected vector. So W2 is equal to, for us, u minus W1, which is going to be the vector 3, -5, 2, minus this projection vector I just got, 14/9, 2/9, -4/9. And then when you do vector subtraction here, you're going to have 3 minus 14/9, -5 minus 2/9, 2 minus a -4/9. And then you do the arithmetic here. And I get 13/9, -47/9, and 22/9 as my result. Please do not annotate my screen. Can you erase that, please? Thanks, Hayden. Do you have a question? Letter C says, give the scalar component of the projection of u onto v. So the scalar of u onto v is equal to the dot product divided by the magnitude. This is where you won't have the magnitude squared, so you will have a square root in your final answer. We already got the dot product. It was 12. And then our magnitude of v was square root of 54. I won't give you full credit here. Why not? I want you to always not rationalize your denominators. I want your denominators to at least be simplified. And since 54 is 9 times 6, and the square root of 9 is 3, you can simplify your radical as 3 square root of 6. And then further, you can now reduce this to lowest term, and your final answer is this scalar, 4 divided by square root of 6. And we're done with letter C. I want to point out something before I move on to another use of projections. And this helps me memorize the formula. And I do encourage you to memorize this projection formula. When you're projecting a vector u onto the vector v, which vector shows up more frequently in the formula here, u or v?
V.
V, correct. That's kind of interesting because you think that the vector u, who you are, he's the guy you're projecting, you think he would show up more often, but he doesn't. He shows up the least in the formula. That's kind of interesting to know and good to keep your eye on, because I've seen students when they are trying to do a projection problem and they haven't practiced enough or whatever, and they accidentally do it backwards and they give me the projection of, say, v onto u, and I can't give them any credit because that's a completely different vector. Let's do a physics example, and yes, this will be on quizzes and exams. So I'm going to draw a picture, and then I'll do like the force diagram for it. So take a look at this one. It's a word problem. Ooh. So we have a 600-pound boat and trailer, and they're sitting on a ramp that's inclined at 30 degrees. So I'm going to try to draw this the best I can.
Excuse me, can you go back a bit? I sort of missed one part about B.
Hold on a second. So we have this 30-degree ramp like this. And I'm not really good at drawing, as you saw last time, but I'm going to do my best. Let's say you have a boat and it's sitting on some trailer here. Well, you know, it's got wheels. I know, it's pretty sad. Okay. If you can imagine the boat and the trailer together weigh a grand total of 600 pounds. Woo. So there's a force vector, force due to gravity, a force vector that I'll just call F, that is the combined weight of the boat and the trailer, okay? And the questions they're asking us, let's take a look at those. What force would be required to keep the boat from rolling down the ramp? So before I draw the vector for that, because it is a force vector, it would be, let's say this trailer is in danger of rolling down the hill and crashing your boat. And let's say you had to stand here and push real hard, and you're pretty strong here, to prevent the boat and trailer from rolling down the ramp. What, you know, how strong do your muscles need to be? You know, how much force would you be required to push back so you don't get run over? So that's what they're asking for in part A. Oh, that seems pretty weird. Yeah, it is. And so what it turns out to be, visually speaking, is it's the force vector F projected onto the ramp. So if you were to shine a bright sun here, let's say sun were able to shine from the ground up. I didn't get where this ramp is considered the ground. What would the shadow that this force vector would make on the ramp. This is projection, so I'm going to try to draw it here. This pink vector here would be your W1. It would be the projection of the force onto the ramp. We're going to get a ramp vector in a moment, but not yet, okay? Now, letter B, they want another force, another vector. They want a vector indicating what force that the tires have to take on, because, you know, they're getting tired holding up the trailer and the boat. So if the tires had feelings, you know, what force would they be feeling that's weighing them down? And that would go straight into the ramp like this green vector here, that's W2. Okay, it's exactly perpendicular to the ramp. And it turns out that, and this is what we're doing here, and this is what our physics brethren do, we basically are resolving that F force vector into the sum of W1 and W2, where that sum gives you back your force vector, and W1 and W2 are orthogonal with each other. W1 is parallel to the ramp because it's going to be a projection of the force onto the ramp, and the W2 is exactly perpendicular to that ramp. Okay, so now that you kind of have a feel, what about the ramp? See, nobody gave us a ramp vector. This is the confusing part for students. They're like, hey, they didn't give us a ramp vector, so how am I supposed to project the force onto the ramp? Good question. You're going to create a ramp vector. Well, how do I do that? You're going to make one up, but it's going to be an educated making it up. So I claim that if you did overlay an X and Y coordinate system right over here, which and you can move it anywhere you want, this little ramp vector, well, in fact, we're the boss. We're going to make him a unit vector. What's the magnitude of a unit vector, folks?
1.
Thank you. So we're the boss. We're going to make a vector that lives on the ramp, and we're going to say, hey, we want it to be a unit vector since it's, you know, easier to deal with. Although it doesn't matter if you wanted to come up with a ramp vector that was 5 units in length. This problem will still work out to the same final answer. Okay, it won't matter. So I'll call this unit vector U because it's easier. Now, the magnitude of this unit vector is 1. And the angle that it makes with the positive x-axis is 30 degrees. So we can easily use this resolution of a vector into its components. This works for 2D vectors only. Be careful. 1 times cos 30 degrees, 1 times sine 30 degrees. And so the ramp vector is kind of easy peasy. It's simply going to be what?
Square root of 3 over 2, 1/2.
Square root of 3/2 and 1/2. Good. Excellent. So there's your ramp vector. And he's the one you're going to do business when you project your force vector onto your ramp. So we're really going to do this. Project F onto the ramp. And it's going to give us visually the pink vector. And once we find the magnitude of that projection, that's the force that you would be required to push back on the boat and the trailer so you don't get ran over. So the projection of F onto U is going to be a scalar times a vector. Now remember, U is going to show up more often than the F. U is here. You're going to have the magnitude of U squared down here. And you're going to have, in the numerator, you're going to have F dot U. Now, what is the magnitude of U again? Just because we were the boss and we decided what it was going to be?
1.
1.
So what does this denominator end up being? Easy peasy.
1.
Yeah, that was kind of convenient. And it's convenient to choose your ramp vector with a magnitude of 1, so you don't have as much yuckiness. Now, what about this force vector? Because it's headed straight down, and they told us that the weight is 600 pounds, the component form is 0, negative 600. So when we take the dot product of these two vectors, you know, you're going to have 0 times square root of 3/2, which is 0. and then negative 600 times 1/2 all over 1 times the vector u. And so the dot product is going to end up being negative 300. And you're going to multiply it with this unit vector. Now, to finish out letter A quickly, I'm going to use a formula from a previous theorem that said if you need to know the magnitude of a scalar multiple of a vector, an easy peasy way to do it if you're kind of lazy is simply to take the absolute value of the scalar and then multiply that by the vector itself. And I'm going to use this to help me get that. Well, how come? Because now when I go, I want the magnitude of this projection of f onto u, which means the magnitude of negative 300 times this unit vector. I already know that this magnitude is a 1, right? And so this magnitude is just going to be the absolute value of negative 300, which is 300. And voila, we have the final answer for letter A. You're going to have to stand there and push with a 300-pound force against the boat and the trailer so you don't get ran over.
Quick question.
Mm-hmm.
So for the reason why the vector for the force, I guess, the F, the reason why it is 0, negative 600 is because the weight is pushing down, right, due to gravity?
Yeah, like if you were to overlay an X and Y coordinate system right over here, and you're the boss, you can overlay it wherever you want, like this. Do you see it's pushing down in the negative Y axis direction?
Yeah.
And they gave you the magnitude. And so you could go, well, the angle is like negative 90 degrees. Sure. Then you go 600 cos negative 90, but that'd be 0, comma, 600 times sine of negative 90, which would be 600 times negative 1.
Okay. Thank you.
Wait, why is u a unit vector or the ramp vector?
You can make it a larger vector if you prefer. I make it a unit vector because it's easier to do business with, but you're not limited like that. There's no hard and fast rule that says the ramp vector must be a magnitude of 1. Nowhere does it say that. I just had to come up with a ramp vector, and because I had to come up with one, I decided it would be easier to make it a unit vector.
Okay.
Let's do part B. Part B, you're basically being asked for the orthogonal component of F in the direction of the ramp. So you're going to use subtraction. It's going to be easy. You're just going to take this force vector and you're going to subtract this vector here. But if I were you, I probably would distribute your scalar because first, because you know, PEMDAS for vectors, it's just easier. So if you do distribute your negative 300, you'd have negative 150 square root of 3 after reducing, and negative 150 like so. And now subtract those two guys. So you're going to go get 0 minus a minus, that's a plus, comma, and then negative 600 minus a minus 150. And then I get, positive 150 square root of 3 for the first component, and for the second component, negative 450. And then, since they want the magnitude of W2, you're going to go get the square root of the sum of the squares, punch that up in a calculator, and I'm going to really round it off to the nearest whole pound here because they asked. And it's about 520 pounds, and that's the force that the tires are withstanding, perpendicular to the ramp. And we're done with this problem. Let's do another physics application of while we're here with working with dot products. Now, if you've already taken physics, some of these force diagrams are kind of obvious, but if you never have, then it's new for you, and that's okay. And you may be a little uncomfortable, but work it out and do some more practice problems. What about work? Well, sometimes doing this class feels like hard work, right? I mean, yeah, there's a lot to do, but you can do it. I've had many people survive this class. So I want to do an easy peasy version of work that usually never happens, but I want to start off easy, and then we're going to get to the real deal. Later on in the semester, when we get really involved into the vector calculus module of this course, like way out in November, we're going to revisit work, but in a different way. We're going to look at work done by vector fields on objects. But this formula I'm about to do is still in operation, even way out there. Okay, so I'm going to do a picture. Let's say you have a big piece of granite. Oh no, another piece of granite like last time. I know, let's say it's really heavy. Okay, and let's say here's the ground. And let's say the granite starts here at point P, and someone is going to try and pull with a force of F that's parallel to the ground and try to move the rock. And let's say they were lucky and they moved it a little ways. And let's say it ended up over here where this vertex here is at point Q. Fine. So what is the work done by the force on the object? Okay. So work, which is not a vector, so you don't put an arrow on top of it. It's a scalar. It is found by taking the magnitude of the force that you're applying times the distance that the object moved. Okay, so for this picture I have, it would be magnitude of F times, and then the distance moved is the distance between P and Q. But a quick and dirty way using vectors would be to form the vector PQ and then just take its magnitude, and that'll give you the distance that the rock moved. Yay! And there's an easy work formula. Now, it turns out you're probably not going to ever use this work formula. Well, why not? You went through all that trouble to give it to us. Because usually you're not lucky enough to get the force in the same line of motion as the movement. That rarely happens. So this formula will work as long as the magnitude of F and the magnitude of PQ are parallel. But usually that's not the case. So let's do the real deal. So same rock. Here it is. I'll put it drawing today. Here's your same rock. Let me draw it the same size. Same rock. He's still starting off here at point P. And let's say the force is a little bit off kilter. So it's not in the same line of motion. It's not parallel to the ground, okay? Let's say it makes an angle of theta with the horizontal. So then what is the work formula now? Well, it's the component of force that is in the same line as the motion. So it's going to be a projection. Ooh, yeah. When we project the force onto the horizontal, so this red vector is the projection of F onto PQ. The work is going to be the magnitude of that projected vector times the distance moved. So let's say the rock or the piece of granite or whatever it is, let's say it moved over here again where Q. So the distance is still going to be the magnitude of PQ. And this is the formula that's more traditionally used because it handles all the cases of the force vector when it's, in alignment with the ground or not. But you're not going to use this formula either. Oh, wait a minute. This is another formula you're giving us that we're not going to use? I know, right? I'm just being so misleading today. I apologize for that. But I don't want you to have to work too hard, so I'm just doing the derivation for you. I'll get to the formulas that you actually will use. So how do you get this projection of F on the PQ? The easy peasy way, in case they didn't give you much info. So let's say they just gave you the magnitude of F and they gave you the angle that F makes with the horizontal. Let's say they're the only two things you have. You can't use the projection formula on the previous page here because that requires component form and you don't have either here. But here's what you do have. You do have knowledge of trig. And trig says, hey, cosine of an angle is adjacent over hypotenuse, right? And if I look at this right triangle, if I drop a vertical down of the F to the horizontal there, the length of this adjacent side leg here is exactly the magnitude of that projected vector. So what I'm saying, folks, is cosine of the angle is the adjacent side leg, which is the magnitude of the projection of F on a P2, which we wish we had, divided by the hypotenuse of the right triangle, which we have, its magnitude of F. Solve this little formula for the magnitude of the projected vector, and voila, you're going to substitute this in place of this red projection magnitude. So one of the formulas I'll be totally okay with you using for work would be W work is cos theta times magnitude of F times magnitude of P2. So that represents the distance the object moved. And there is a dot product form. What? There's another format? Yes. This right-hand side should remind you of a formula that we did when we started talking about projections. Take a look at this formula, the theorem, the angle between two vectors, and the alternate version. Look at the alternate version in particular. You notice it looks like cosine theta times the product of two magnitudes. So what if you use this alternate formula in reverse, like use it backwards? You can say that it's equal to a dot product. Well, what does that have to do with what we're doing right now? A lot. And we're going to apply that alternate version of the theorem backwards to get an alternate form for work. So the alternate form for work, which is the dot product form, it's the dot product of your force vector with a vector PQ. So which one are you supposed to use when? It depends. You'll know by reading the word problem and looking at the information provided. So we're going to do two work problems here. Let's see if you can delineate which of the two work formulas given here in this definition will be applicable. All right, we'll start with letter A here, example 5. To close a sliding door, a person pulls on a rope at a constant force of 50 pounds at a constant angle of 60 degrees. Find the work done in moving the door 12 feet to its closed position. Be sure and give the appropriate units. Any ideas on which definition should I use? One or
Projection. One.
two? Yeah, how'd you know?
60 degrees.
Good, yeah, they gave you like an angle and they gave you some magnitudes, 50 pounds and 12 feet as a distance. So you're like, yeah, I'm gonna go cosine 60 degrees times 50 pounds times 12 feet. What is cosine of 60? Isn't it a half? And multiply this all out and you'll get 300 what? Foot-pounds. Foot-pounds is actually work units. I'm not making this up. Foot-pounds, not pound-feet. It's foot-pounds. Foot-pounds. Work.
I have a quick question.
Sure.
So they already gave us PQ because it already said the distance it moved, right? Okay.
Yeah, because if you look at this work formula, it's your magnitude of your force, or the projected, it's the component of force going in the same direction, times the distance. And so the distance the door moved was 12 feet, yeah? While we're here, if I go back to this boat sitting on a ramp, and this is kind of a trick question, but is there any work done by the boat on the ground, say?
Yeah. Maybe, yeah.
Maybe. So here's the question. is this boat, if, just say it wasn't rolling, is the boat moving?
No.
Not moving any distance. So if there's no distance being moved, there's no work being done. I know that seems like a trick question, but when you take physics, they may try to trick you on a test or a quiz. I know my physics prof did, and I blew it. But if there's no distance or movement of an object, even though there might be some forces involved, no work will be done. There has to be some distance the object moves in order for work to be calculated. Ah, well. All right. How about this one? By process of elimination, we're going to use the second version of the work definition here. We're going to need the dot product, and they give us enough information. We're moving the object from point P to Q, and they're giving us the force vector in component form. So we're going to first have to get the PQ vector, and don't forget terminal minus initial, terminal minus initial, terminal minus initial. So that's -3 minus 1. 0 minus a minus 1, -2 minus 2, and I get -4, 1, -4, and then work is F dot PQ, and so you're going to take your work vector to -4, 3, dot product with -4, 1, -4, and 2 times -4 plus -4 times 1 plus 3 times -4, whoopsie daisy, and I get negative. Can you have a negative amount of work done? Yep. You can have 0, negative, or positive for work. It's a scalar. What are the units here? Are the units foot-pounds for this problem? They said the distance is measured in meters here, so it's definitely not feet. And the force is measured in newtons, not pounds. So there's 2 answers you can give me for units here. I'll be okay with both. Newton meters, believe it or not, that's legit. Or J stands for joules, because joules are Newton meters. That didn't work too well. Joules. J for joules. Same as Newton meters. Okay? The units for work. All right. We are officially done with dot product. Congratulations. Ooh. Oh, interesting. Oh, here's all my stuff. You can't live with it and you can't live without it. Isn't that the truth? So we're going to do the cross product now. We're in the next section. So here we're going to take a look at another way that you multiply vectors. Not to be confused with the dot product though. This is called the cross product. And they're 2 very, very different concepts. So you want to make sure you keep them straight. Otherwise you might be making a silly mistake. Okay. Cross product. Okay, the definition of a cross product of 2 vectors in space. What does space mean again? Quick.
3D.
Exactly. Thank you. Yep. 3D. Now, it turns out that cross product is very restrictive. You can only do cross product in 3D. There's no such thing as cross product in 2 dimensions or 4 dimensions or 5 dimensions or 20 dimensions. No such thing as cross product. Now, dot product is a different story. Dot product you can do in any dimension. It's valid whatever dimension you're in. with the exception of maybe one dimension. I don't know, maybe you could do a dot product in one dimension. It wouldn't be very interesting. Not that. Okay, let's take a look at the cross product. So the official definition, which you're not going to use to go get it, so but I do want to give you the actual definition is, and you're going to use a little x for cross product, u cross v, is a scalar times a vector, which is going to give you a vector overall. Now the scalar is going to be sine of the angle between the two vectors multiplied with the product of the magnitudes times some other vector here, and this happens to be a unit vector. And the unit vector is perpendicular to the plane containing both u and v, according to a right-hand rule. What the heck is the right-hand rule? If you're left-handed, don't get a resentment. This is the right-hand rule. And so here's a picture. If somebody says, take the cross product of u and v, you notice that u and v can be considered in some plane. So this is sort of flat here, a flat table. Notice this pink vector is making a 90-degree angle with the flat table, the plane containing the u and v vectors, okay? Your right hand swings in. First, have your fingers curl through the first vector they're mentioning, in this case u, and then have your fingers curl all the way around until they're curling through v, and then close your fist, but leave your thumb up. And the direction that your thumb is pointing is the direction of the cross product. I know, weird, huh?
Can I see the equation again?
Is that an n?
That's an n. It says n is a unit vector, perpendicular rather, to the plane containing u and v. Now, folks, I want to be completely straightforward with you here. Let's be clear. You're not going to be using this formula on any of the quizzes and exams. Well, why'd you give it to us? Because that's the official definition. Well, how do we get the cross product then? We're going to get there. Patience. Let's move forward now. The way, more often than not, you're going to get a cross product is by doing the determinant form with cofactor expansion. Well, how's that look? I'm going to show you. If you've already taken linear algebra and you know how to take the determinant of a 3x3 matrix, welcome. You already know this. If you haven't taken linear, don't worry. I'm going to go over this from scratch. So you're going to see these big bars here. This does not mean absolute value, okay? But it's the way we denote determinant in mathematics. The very top row, you're going to put the standard unit vectors I, j, and k. And if I don't see this on your handwritten paper, like you go, oh, I know it's there, and you neglect to write it, you will lose points. Please write it in there. The second row of this matrix we're taking the determinant of, you put the components of the first vector. In the last row, you put the components of the other vector. Okay, that's how you start every time. And don't tell me you do this in your head. Even if you have the right answer, I take away points. So the way you're going to do it is you're going to have, it's going to equal a 2x2 determinant times I hat minus another 2x2 determinant times j hat plus a 2x2 determinant, a different one, times k hat. Well, wait a minute. I thought we're in the middle of trying to do a 3x3 determinant. I know we are. But in order to find a 3x3 determinant, you have to know how to take a 2x2 determinant, which is actually pretty easy, and I'll show you as we do this process. Okay? So what goes in the first 2x2 Here. It's a 2 by 2 matrix. The way you do it is you block out the row and column that I hat lives in, and you look at the numbers that are sort of still there, that didn't get crossed off or blocked out, and write them down. Okay? That's your 2 by 2 guy. I know. Weird. And then the next 2 by 2, by the way, this is a minus here, not a plus. Minus the 2 by 2 determinant times j hat. We'll block out the row and column that j hat even lives in. And then the other components that aren't getting blocked off, write those down. That's your next 2 by 2. And then the last 2 by 2 determinant is found by blocking out the row and column that k hat lives in and looking at the components that aren't getting blocked out. Copy them down. And now you're ready. This is kind of a long algorithm. Stay with me. If you're a computer programmer, any of my computer programmers in the room, you could write some code that would do this algorithm for you. Yeah, cool. So now what? Now I'm going to teach you how to do a 2 by 2 determinant. It's easy peasy. This is just a pure number. It's the pure number that you get by first taking the product of the major diagonal entries, U2 multiplied with V3, minus the product of the entries along what we call the minor diagonal, U3 V2. Okay? That number gets multiplied by I hat. Minus, and now you're going to do the next 2 by 2 determinant. Oh my goodness. So you're going to go that guy minus that guy. So you're going to go U1 V3 minus U3 V1. Yep. Going to be some weird scalar. And multiply that guy with the standard unit vector J. Plus, I'm running out of room here. You're going to do the last 2 by 2 determinant. U1 V2. I have to change colors. Minus U2 V1. Some number there. Don't do this backwards either. Like if you do the minor diagonal minus the major diagonal just by accident, can't give you credit, not even partial. Practice to avoid making silly mistakes. And there you have it. This is a vector. And it's a vector that would be orthogonal to both the original vectors via the right-hand rule.
And so that's the same thing for everyone that we use, since everything's going to be a 3 by 3. So you only can do it in 3D.
Yeah.
Okay.
You can only do the cross product using vectors in space. No such thing as taking a cross product of 2 vectors in the plane, for example. Meaningless. So let's do some cross products. Are you guys ready? Okay, here's U, 1, -2, 1. Here's V, 3, 1, -2. Find U cross V. Fine. So U cross V is going to be found by taking the 3 by 3 determinant. Don't forget to put I hat, J hat, K hat along the top. 1, -2, 1 in the second row. 3, 1, -2 in the third row. So you're going to go 2 by 2 I hat minus 2 by 2 J hat plus 2 by 2 K hat. Now, a lot of students come up to me like after class and go, how come there's a minus here, but there's a plus over here? And the answer to that is it has to do with the matrix of cofactors, and I don't want to get into it, but take a linear algebra class and they will completely answer it for you. Okay? So then if I block out the row and column that I hat lives in, -2, 1, 1, -2 are the 2 by 2 elements. If I block out the row and column that J hat lives in, I get 1, 1, 3, -2. And blocking out the row and column that K hat lives in, I get 1, -2, 3, 1. And now the fun and play, you find the 2 by 2 determinant here. So you go -2 times -2, which is 4, minus 1 times 1. That's just 1. I hat. Minus, and now you're going to do another 2 by 2 determinant here. 1 times -2 is -2, minus the product of 3 and 1. Well, that's just 3. J hat plus, and one more 2 by 2. You're going to go 1 times 1 That's 1. Minus 3 times -2. Well, that's -6. Uh-oh, we have 1 minus a -6. Yeah, there's a lot of negatives running around. Be careful. Silly mistakes can occur. So I get 3i hat minus a -5j hat plus 7k hat. And of course, minus minus is a plus. So I'm going to put it in component form from a final answer just because I prefer it. And I get the vector with components 3, 5, 7. And we're done with letter A. So what about V cross U? I'm going to do this quickly here. First row across the top, IJK. Second row, the components of V, 3, 1, -2. Bottom row, components of U, 1, -2, 1. So you're going to get a 2 by 2 I hat minus a 2 by 2 J hat plus a 2 by 2 K hat. And I get the elements 1, -2, -2, 1. 3, -2, 1, 1 for the second 2 by 2, and 3, 1, 1, -2 for the last 2 by 2. And am I running out of room here? I think what I'll do is I'll append a page. Need more room, help. So the first 2 by 2, I get 1 minus -2 times -2. So 1 minus 4 I hat minus 3 times 1 is 3, minus 1 times -2 is -2. J hat plus 3 times -2 is -6, minus 1 times 1 is 1, K hat. Okay, so what do I get here? I get -3 I hat minus, looks like -5 J hat plus -7 K hat. Wait a minute. Compare this to my answer to part A. How do these two compare? What do you think?
Opposite signs.
Yeah. So what can we say about the relationship between U cross V and V cross U? One is just pointing in the opposite direction as the other. That's all. So visually, what would that look like? Well, with the right-hand rule, we get U cross V. And again, using the right-hand rule, but having your hand, like, I don't know if you guys can see me in the video, you have to turn your hand so that it's pointing down. You first put your fingers through V, then U, and notice your thumb is pointing down. So V cross U it'll still be making a 90-degree angle with the two original vectors, but it's pointing down instead of up. So it's still orthogonal to U and V. Now, what about when you take a cross product of a vector with itself? Well, what the heck happens? Now, if you've taken linear, you probably already have an idea of what the heck's going to happen, because you know about taking determinants of matrices where a row is either equivalent to another row or a row is a multiple of another row. So if you did this, the 2 by 2 method way, the 3 by 3, sorry, you had to find a lot of 2 by 2 determinants here, the usual. Do you see anything weird happening?
It's going to cancel out.
So you get the 0 vector. Does that always happen? Well, yeah, anytime you take a vector's cross product with itself. Can you take the cross product of two vectors in the plane? This is 2D. What did I say about that? Yes or no?
No.
Nope. Meaningless. Well, somebody I know, I had a teacher who made me do it. No, he didn't. Can't do it. It's impossible. Now, what you could do is you can embed two vectors in the plane into a three-dimensional coordinate system, in which case they then take on a third component, where the third component would be 0. Then you could take the cross product of those embedded in 3D vectors in the plane. Sometimes people do that. But that's very different from the statement that there's such a thing as the cross product of two vectors in the plane. I could make this a true-false question, you know, right? So just saying, I'll put true-false questions here and there. Okay, let's do some algebraic properties. Then we'll do some geometric properties. Then I'll prove a little bit, and then we'll do an example. And yeah. And that'll probably take us to the end, roughly. We'll see what happens, how far we get.
You go back to B real quick. Thank you.
Here or up here? Further?
Yeah, a little further. B. I got C, but
Okay, so B started right here, B, and then there's the intermediate step.
thank you.
Got it? Okay. So let's do a quick meme before we do these theorems. This meme, you know, sometimes these memes are fun. I like it. Yeah, those are the days. Okay, some theorems. We're going to fill in the blanks for all these theorems. Let's do the algebraic properties first, and then we'll do geometric properties. Okay, one right after the other. Here we go. So U, V, and W are vectors in space. That means 3D. Woo! 1, 2, 3, 4, 5, 6. Okay, first up, you already know this one. U cross V will be equal to the opposite of V cross U. You even saw that in the last example. Kudos. This one has to do with distributing. If somebody said, hey, take the cross product of U with the sum of V and W, you can do it just like that first. Like I would first take the sum and then I would do the cross product. But if you want to, it's equivalent to U cross V plus U cross W. That's true. Number 3, if you have a scalar and you're multiplying it with a cross product, you can do it like that first. Do the cross product first and then hit it with the scalar multiple. Or you can first do the scalar multiple with U and then take the cross product of that result with V. Or you can take the cross product of U with the scalar multiple of V, whichever is your favorite. They're all equivalent. Going to get you the same answer. Now, what about U cross the 0 vector? This is the only time that commutativity works with cross product, because otherwise you already saw cross product is not commutative. It does matter what order that you do cross product with. Now, dot product is another deal. Dot product, U dot V, same as V dot U. Don't care what order, you get the same thing. Cross product, though, is order dependent. It's not commutative. But if you're taking a cross product with a 0 vector, it won't matter what order. Well, why not? Because your answer is going to be the 0 vector no matter what. Okay. And we already saw the answer to number 5. What happens when you take the cross product of a vector with itself? You get always
The 0 vector?
Yeah. Perfect. And then last but not least, I'll put a little star by this one because it's weird. You'd never guess this one. It's wacky. If you take the dot product of U with the cross product of V and W, it's not what you think, people. Don't try to distribute anything. It's the same as the cross product of U and V dot product with W. I know, don't try to figure it out. This has a special name. This is also known as the triple scalar product. And it also has another name, the box product. We'll see why in a little bit. The box product. You may hear it referred to as that. This one's very special. That's algebraic properties. Now let's talk about geometric. Geometric meaning more visualizing. So let's see,
Professor Reski,
sure.
really quick on the fourth one, or just so I understand that correctly, if you take a vector and cross product it with the zero vector or vice versa, it's going to be the zero product or zero vector?
Yes,
Okay.
every time.
Huh. Okay. I think I
So I
understand it
mean,
now.
let's just say you were going to do it just for kicks and giggles. I'm setting up the I hat, J hat, K hat is the first row. And let's say you had the components U1, U2, U3 is the second row. And you'd have all zeros in the bottom row. Can you see right now, just even before you start writing it all out, why everything would get zeroed out?
Yes, I can see it now.
Great. Okay. I hope that answered your question.
Yes, it does. Thank you very much.
Fantastic. All right, now you ready for the geo? Here we go. You got two non-zero vectors in space because you know zero vector is not interesting. It's just a dot. We want our vectors to have some oomph, some magnitude. And let's say theta is some angle between those two vectors wherever they are. Fine. And you already should know this is true because I showed you the picture on the very first part of today's lecture. When you take the cross product, U cross V, it is a vector. And that vector is orthogonal to both U and to V. It's making a 90-degree angle. It's perpendicular to both U and V. And if you don't believe me, go back to the picture. My bird is crying. Too far. So I hope you can see from this picture that this cross product here is definitely making a 90-degree angle with both U and V. So it's orthogonal to both. That's what's so cool about it. Yeah. That's really awesome. Okay, let's do number 2. The magnitude of U cross V is sine theta magnitude of U times magnitude of V. Now this right-hand side is a scalar that I actually showed you on the first page of today's lecture. It was the scalar multiplied with the n, which n was a unit vector pointing in the direction of a vector orthogonal to U and V. So that's where that shows up again. It's the magnitude of the cross product. Now, I love number 3 because it's really cool. What if you took the cross product of two vectors, U and V, and they're not the same? I mean, they're two distinct vectors. And you actually get the zero vector. Can that happen? Yes. Well, I thought you said that only U cross U is 0. I never said that. U cross V can also equal the zero vector if and only if, IFF is short for if and only if, U and V are scalar multiples of each other. Does anybody remember when two vectors are scalar multiples of each other, what the relationship is? Starts with the letter P. And it's
Parallel?
yes, parallel. So why do I put a star by this? Because one of the ways you can figure out if two vectors are parallel is if you look to see if one's a scalar multiple of the other. We did that in a previous lecture. But if they're 3D vectors, another cutesy way to tell if two 3D vectors are parallel to each other instead of figuring out if they're scalar multiples or not, is just take their cross product, and if you get the zero vector, they're parallel. Cool. Okay, I'm just excited. It's kind of a neat fact. Could be a good true-false question, I'm just saying. Number 4, when you do take the cross product's magnitude, U cross V's magnitude, the geometric interpretation is you get the area of a parallelogram having U and V as adjacent sides. That's kind of cool. And I'm going to prove that one right now because it's just so cool. Let's look at a picture. Let's say here's U. Oh, it's not a very nice vector. Here's U. And let's say here's V. And if you can imagine that being a parallelogram, if I supply the missing sides with dotted lines. So those two vectors are adjacent side lengths. Now, I don't know if you remember the area of a parallelogram from some previous math class, but it turns out that it's base times height. Base times height. And that is not a cross product there, that's just time. So the base would be the length of the leg or the, the side that's on the ground. Okay, so that would be like the magnitude of U here. And if you drop a perpendicular from the vertex there of V down to the base, this is the height. It's not the magnitude of V. It's the length of that line segment when you drop a perpendicular from the tip of V down to the base. So that would be your area right there. Well, darn, I do have the base. That's just going to be magnitude of U. But then how do I get this height? We'll call it H. So if you can imagine the right triangle that I'm sort of creating here, there's a right triangle. And what do we know? We know that sine theta from trigonometry is opposite over hypotenuse, okay? And theta would be the angle that U and V make with each other. So what I can say here is sine of that angle, theta, would be the opposite side length. That'd be my H, my height that I wish I had, divided by the hypotenuse, and that is simply the magnitude of V. So if I solve this formula for H by multiplying both sides by the magnitude of V, I finally have my height. So I can substitute it right here. So what do I have now for my area? Because that's not looking like what I need. Well, it is an alternative though. You're going to have your magnitude of U times sine theta times magnitude of V. If I rewrite this so it looks a little prettier, let's put the sine theta in the front so it doesn't look so yucky. And the product of the magnitudes U and V. Fine. Now what? Well, now look at property 2. I'm going to use property 2 backwards. I'm going to use it going from right to left, and I'll replace this sine theta product of the magnitudes with its equivalent, which is the magnitude of U and V. Ding, and I'm done with the proof. Yay. So by property 2, we were able to prove property 4. Okay, I still got a little bit of time. I'm going to use it. I'm going to go for like 9 or 10 minutes and then I'm done. These are easy, these next few problems. Piece of cake. It's a good way to finish it out, just to kind of do some cleanup. I'm not going to finish completely the cross product. I'll save torque till next time. and then we'll finish it out. So take a look at this problem. You got a couple of space vectors. How do you find a vector that's orthogonal to both vectors? How will we do that? Any ideas?
Take the cross product.
Yes. Bingo. Yep, U cross V is the answer because that's the definition of the cross product. It is a vector orthogonal to your two originals. Yay. Success. So I'm going to put IJK on the top row, -3, 0, 1 for row 2. That's the components of U, and then 2, 2, 2 for the bottom row. And then I'm going to do a 2 by 2 times I hat minus a 2 by 2 J hat plus a 2 by 2 K hat. And each of these 2 by 2s can be found by blocking out the row and column of the unit vector that it's corresponding with. Then I do these 2 by 2 determinants. 0 times 2 is 0, minus 2 times 1 is 2 I hat, minus -3 times 2 is -6, minus 2 times 1, okay, -6 minus 2j hat, plus -3 times 2 is -6, minus, well, 0 times anything is 0, right? And then, ooh, what do I get here? Yeah, I'm going to put it in component form because it looks prettier. Brackets, -2, comma, +8, comma, -6. Okay, and that is a vector orthogonal to both of the original vectors. Now, letter B, find the area of the parallelogram with sides, two adjacent sides, U and V. Well, wait a minute, didn't that last property say that the area of a parallelogram is just the magnitude of the cross product? Sure. So we go and get the magnitude, and we already got the answer from letter A, so let's not do that one over again. Square root of 2 squared plus 8 squared plus 6 squared. Whew. What's 4 plus 64 plus 36? Square root of 104. That's the answer, but I'll take away 1 point just because I want a little extra cleanup. Well, what do you mean? 104 does have a perfect square factor. I know. It's 4 times 26. And hey, square root of 4 is a nice number. Hey. So there's your final answer. 2 times the square root of 26. That's the answer for letter B. That's the area of your parallelogram. Now, here's the weird one. I didn't give you this answer, but it's going to be on quizzes and exams. What if somebody says, hey, find the area of the triangle that has sides U and V and then U minus V? Can you guys see that that triangle is actually half of the parallelogram with adjacent side lengths U and V?
Yeah.
So anytime you're asked for the area of a triangle with side length U and V, you just take half of the area of the parallelogram with side lengths U and V. But that would be half times the magnitude of U cross V. But we already got the magnitude of U cross V from the previous part. That was 2 square root of 26. So what's half of 2 times square root of 26 after reducing?
Square root of 26.
Yep. And we're done with letter C. Yay. And I put a little infographic here for you so you'll never forget how to find that area of a triangle. Example 3. So let's say U and V are space vectors, and you're given a couple magnitudes and the angle between them as shown. So this is supposed to be a 120-degree angle. Fine. How do you find the magnitude of U cross V when we can't even get the cross product because they didn't give us component form? And don't try to resolve in component form. Well, you told us it's magnitude times the angle. Yeah, that's the angle it's making with the positive x-axis, not the angle with each other. I don't want you doing that. That's a mess. Instead, you're going to use property 2 in the geometric properties. What does property 2 say? Look at it. We'll write it down again, don't worry. So property 2 says if they give me all the right ingredients, I can get this magnitude of the cross product. And they gave me all the right ingredients. I've got an angle. So they take the sine of that angle. And then I have the product of those magnitudes. And then I think sine of square root of 3 halves. I think it's square root of 3 halves. It's 120. And then without the calculator, I got the magnitude is 375 square root of 3. Now this one's hard. I get a lot of students who freak out when I ask them one of these right-hand rule problems. But you need the right-hand rule to do letter B. So everybody whip out your right hand. Woo! Got it. Follow me, and I'm up here on the video screen. If we were in person, this would be so much easier to do. But I have to kind of get my body sort of behind my paper, I don't know, which is my computer. And I first put my fingers, you know, sort of curling them around, put them through V first, because it says V cross U. Then put them through U. And then I noticed that my thumb is sticking out, and it would be sticking into the paper, not out of it. So the answer is into the page and not out. What about out of the page? Well, U cross V, if I first stick my fingers through U and then stick them through V, my thumb, and then make a fist here, would be sticking up out of the page if I did U cross V. But V cross U is into the page, okay? And yes, it matters. When you take a physics class, I remember taking a final in physics when I was at UC Berkeley. And it was a huge class. There were like 300 people in this huge room. It was terraced, you know, it was like theater seating. And it was a 3-hour final. And I remember halfway through the final, I needed to take, my eyes needed to take a break because it was a hard exam. And I just kind of looked around at everybody in the room, and like half the room was doing, contorting their body and going like this, and, you know, and I just burned that visual in the back of my brain. I thought, I always want to remember this day. And I silently smiled to myself. That was interesting. And so I'll share that little visual with you of 300 students trying to do the right hand rule and like moving their bodies in these little tiny chairs. Hilarious. Okay. True or false? Let's finish with this one, and I'll save letter D for later. True or false? The dot product of U with a cross product U cross V is the scalar 0. True or false? If it's true, explain why. If it's false, explain why not, and give a counterexample, or, you know, that's how you do true falses. You got to give an explanation.
I'm gonna go with false.
Okay, that's one way. Let's look at a picture. When you take the dot product of 2 vectors and you get 0, what does it mean those 2 vectors relationship is? You guys remember that?
Parallel.
If U dot V equals 0, what's true about
Orthogonal.
V? Yeah, U and V are orthogonal, which is a fancy word for perpendicular. So you need this fact. That's true. That's true. But they're asking U dot product U cross V. Is that equal to 0? Now, what is that saying? That's saying, if it is true, here's what would have to be true. That this vector and this vector are orthogonal. Are they? Look at this picture here. Here's U cross V. Here's U. By that picture, are those 2 guys orthogonal?
Yes.
Yes. So true. By definition, of what it means to be a cross product. Cross product, if you look even back at the original definition here, this U cross V is going to be a vector that's perpendicular to the plane containing U and V, and by default to those vectors U and V. You're guaranteed. So based on that, if I gave you another problem, true or false, and I'll leave you with this. What if you took V dot product with the cross product? Is that equal to 0? Also, I'll give you a hint.
Yes.
Yes, also true. Yay. Success. So you got a little introduction to cross product today. Congratulations.